Welcome to Engineering Mechanics video lecture. In this lecture I am going to explain you about a solution for a problem related to kinetics of rectilinear motion. I read the problem one time. Two blocks of weight W1 and W2 are connected by a bar of negligible weight and rests on an inclined plane having inclination angle alpha equal 30 degrees as shown in the figure. Find the acceleration of the system and induced force in the bar when the system slides down the plane. The following data are given: W1 equal 50 Newton, W2 equal 100 Newton, mu1 equal 0.1 and mu2 equal 0.2. For the given problem, this is the problem figure. On the inclined plane, two blocks are placed. Those blocks are connected by means of a negligible bar, weight of bar. When they are sliding down the inclined plane in this direction, we can find the acceleration of the moving blocks W1 and W2. Okay, considering the problem condition, we are going to draw the free body diagram of W1 and W2. Considering the force generated in the bar is a tensile T of magnitude. Weight of block 1 given as W1, weight of block 2 given as W2. From the basic definition of weight, we can write weight 1 equal to m1 into g, where m1 is mass of the block W1, g is acceleration due to gravity. By following this equation, we can find mass of the block W1. m1 equal to W1 divided by g. In the same way, we can find the mass of block 2 or W2. W2 equal to m2g. By following this equation, we can find mass of block 2 or W2. m2 equal to W2 by g. Mass of these two blocks used to find the inertia force generated opposite to the direction of sliding down the inclined plane for each and every block. When the block W1 and W2 moving down the inclined plane with acceleration small a, the generated inertia force opposite to the acceleration direction or direction of motion can be written as mass into acceleration for two blocks. For the block 1, inertia force is exactly equal to m1 into a, which is exactly equal to W1 by g into a. For the block 2, the inertia force is m2 into a equal to W2 by g into a. While these blocks are sliding down the inclined plane, at this contact surface, frictional force will be generated opposite to the direction of sliding. Sliding taking place in this direction, frictional force is directing in this direction, opposite to the direction of sliding. At the contact in between W1 and surface, inclined surface, and W2 and inclined surface, we have to introduce normal reaction force perpendicular to contact surface, like in this fashion. R1 reaction force, R2 reaction force we have to introduce in the free body diagram. Weight of each block directing downward direction in this direction perpendicular to horizontal ground for W1 and W2 block. Okay, considering all these forces, we have to draw the free body diagram for W1 and W2 separately. This is the free body diagram of black W1. The angle in between weight of the black and normal reaction force R1 is alpha. This is the angle of inclination in between inclined plane and horizontal ground, alpha. This is a tensile force generated in the string. R1 is normal reaction force. Weight 1, W1 is weight of the black one. W1 by G into A is inertia force. The direction of inertia force is opposite to the direction of motion. Okay, while this black is sliding down the inclined plane, we can consider this is the inertia force direction. Okay, at the contact surface also we have introduced frictional force by following the coefficient of friction mu1. F1 equal to mu1 into R1. The direction of this force also opposite to the direction of motion, direction of sliding. As this weight force is alpha inclination with normal reaction force, for this W1 force we can find vertical component and horizontal component. Okay, for this alpha angle, this is the opposite component, this is the adjacent component. W1 cos alpha is adjacent component, W1 sin alpha is opposite component for this alpha. For the black 2, when it is sliding down the inclined plane in this direction, opposite to sliding direction we have to introduce inertia force. The magnitude of inertia force is W2 by G into A. At this contact surface we have introduced normal reaction force R2. In between normal reaction force R2 and weight force we have to consider alpha angle of inclination. By following this angle for this inclined weight force we can estimate opposite component W2 sin alpha. For the same W2 inclined force we can find adjacent component W2 cos alpha. Okay, at the contact surface in between black 2 and inclined surface, while it is sliding down the plane, we have to introduce frictional force opposite to the direction of sliding. That is F2 equal to mu2 into R2. Okay, this is the string tension T. Considering free body diagram of W1 and W2, we are going to write the equations of dynamic equilibrium along the direction of sliding. In the equation of dynamic equilibrium we can consider the force which is directing along the sliding direction of sliding or along the acceleration direction can be considered as positive. Okay, W1 by G into A is directing opposite to the acceleration, so we can consider this as negative. Tension force is directing along the direction of sliding in the direction of acceleration, so T considered as positive. F1 equal to mu1 into G, frictional force, is directing opposite to the direction of sliding. This is direction of this frictional force is opposite to acceleration, so this is also considered as negative. Okay, component of weight for alpha, this is the opposite component. This is also directing along the direction of sliding, along the direction of acceleration, so this force considered as positive. Okay, writing the equation of dynamic equilibrium for the black W1 along the direction of sliding. This is the equation: T minus mu1 into R1 plus W1 into sin alpha minus W1 by G into A equals 0. When you write equation of equilibrium along the perpendicular direction of motion or perpendicular to direction of acceleration, we can get normal reaction force R1 and double 1 cos alpha in the equation of equilibrium. R1 minus double 1 into cos alpha equal 0. From the second equation we can find R1 value, normal reaction force for the black one, as R1 equal to W1 into cos alpha. When you substitute this value in the first equation of equilibrium, we can get new equation. This is the final equation for the black W1. T minus mu1 W1 cos alpha plus W1 into sin alpha minus W1 by G into A equals 0. Then after writing the equation of equilibrium, dynamic equilibrium for the black W2 along the direction of sliding. T is a tension force in the bar directing opposite to the acceleration, so we can consider this as minus T. Inertia force is also directing opposite to the acceleration direction or direction of sliding direction. Okay, the direction of frictional force also opposite to the direction of sliding or direction of acceleration. So this is also considered as minus. W2 sin alpha is directing along the direction of sliding. So we can consider this as positive. From this free body diagram of black W2, we are getting only one force, W2 sin alpha, is getting positive. Frictional force is negative, tension force in the bar is negative, inertia force is also negative. These three forces are opposite to direction of sliding, direction of acceleration. This is the equation of equilibrium along the direction of sliding for the black W2. Minus T minus mu2 R2 plus W2 sin alpha minus W2 by G into A equals 0. When you write the equation of equilibrium along the perpendicular direction of sliding or direction of acceleration, we can get in the equation of equilibrium R2 force and W2 cos alpha force in the equation of equilibrium. This is the equation of equilibrium. R2 minus W2 into cos alpha equals 0. From the fourth equation we can find R2 as R2 equal to W2 into cos alpha. When you substitute this R2 value in the third equation, we can get, this is the final equation, minus T minus mu2 W2 into cos alpha plus W2 into sin alpha minus W2 by G into A equals 0. Considering this as a final equation for the black W2. When you add these two final equations for the black W1 and W2, we can get the acceleration of the system. This is the final equation for the acceleration of the system. Small a equal to W1 plus W2 into sin alpha minus of mu1 W1 plus mu2 W2 into cos alpha into G divided by W1 plus W2. According to given problem, we can consider W1 as 50 Newton, W2 as 100 Newton, mu1 as 0.1 and mu2 as 0.2. When you substitute these in the acceleration equation, we can get acceleration of the whole system as follows. A equal 0.355 into G. When you substitute acceleration of the whole system in any one of the final equation, 1 or 2, we can estimate the tensile force generated in the bar. We can estimate that value by following second equation as follows.